In this video, we'll implement one of the most popularly used sorting algorithms, the heap sort. The idea behind it is to fill each spot one by one from right to left. For example, here I would fill it 10, then 9, then 8, then 7, then 6, then 3, then 2, and then 1, until it is sorted. But the problem is, how do we find the maximum each time efficiently? One way to do this is using selection sort, which unfortunately is too slow. Selection sort finds the maximum value by searching through every single element and picking the maximum one. I have implemented selection sort in Java at the right. This is where the Max-Heap data structure comes in. A Max-Heap is a full binary tree where every node is greater than or equal to both its children. Therefore, the root has the greatest value. The first step is to construct a tree from the original array. And we do this in a particular order. And the order is root, then left child, then right child, left child of left child, right child of left child, left child of right child, and right child of right child, and so on. So the root is the variable at index 0. The left child of each index I of the original array is at 2i plus 1, and the right child is at 2i plus 2. The parent of each child I is at floor I minus 1 divided by 2. Now we can implement these methods in Java. First, I'm going to implement the left child method. So that is just a function, takes in parameter I and returns 2 times I plus 1. Right child will be similar, except we're going to return 2 times I plus 2. And parent, we're going to return math floor I minus 1 divided by 2. Now we have to build a heap so it actually satisfies the Max-Heap properties. We have to move down every node that has less value than one or both of its children. We find the node with the greatest value between the node, its left child, and its right child. And if that value is not the node, we swap it with the node and continue the process. This method is called sift down and is sometimes also called heapify. And we'll call this method for every non-leaf, which are all the nodes that have at least one children. And these are all the elements from indices 0 to math.floor array.length minus 1 divided by 2. And we're going to start from the end and work our way up to the root. So let's see how this works. So first, the lowest non-leaf element is 9. And there's no change because 9 is greater than 6. We sift down 2, which swaps with 10, the greater of its children. Sift down 7 swaps with 9. 1 swaps with 10, and it swaps with 8. And now we have our fully built Max-Heap. Now we can implement the sift down method and build our heap. The sift down is going to be a void method. And for parameters, we'll take in an array of index I, and we'll also have a boundary. And this is going to be important when we actually do our sorting, where we're going to have an unsorted region and a sorted region. And we don't want to mix the two. But for now, the boundary is just going to be the length of the array minus 1. So we can declare a few variables. L is going to be the left child of I. R can be the right child of I. And the maximum index between the three, max I, is going to be set as I. We're going to check if L is less than or equal to boundary. So does I have a left child? And if array L is greater than array max I, then we're going to set max I to L. If it also has a right child, so if R is less than or equal to boundary, and array R is greater than array max I, then we'll set max I to R. Finally, at the end, we'll check if max I is not equal to I, that means the heap property was violated, then we're going to swap them. So in temp is going to be array max I, array maxi is array I is temp. So we're just swapping array maxi with array I. And we're gonna repeat this process, shift down on maxi. Now we can build our heap. So I'm gonna initialize a scanner. And a variable n, which is gonna be the size of our array. And I'll initialize an array, which is going to have size n. And for every index in the array, we're going to set array I to scanner dot next int. And now we can build it. So we're going to start at the lowest non-leaf, which is going to be at math.floor n minus 1 divided by 2. We're going to go until the root, so while I is greater than or equal to 0. And we're going to decrease I by 1 each time. And in here, we're going to shift down I. And for our boundary, we're going to have n minus 1. And then for every value in the array, we can print it and space at the end. So if we run this, we're going to enter the number of elements, which is 8. And this is the array I used as an example. And you can see that we got the same result as we did when in the presentation. Now we need to actually sort it. So to do this, we'll run a bunch of extract root operations. And it is pretty simple. We just swap the root with the last element in the array. And we move the root into a boundary into the sorted region. And we call shift down on the root. Then we decrease the boundary by 1 and repeat this while the boundary is greater than 0. By the end, we'll get a sorted array. Let's see how this works. So again, this is our fully built heap. And first we're gonna swap the lowest value, the last element in the array, which is 6, with the root, which is 10. And we're gonna move 10 into our sorted region like this. Then we're gonna shift down the root, and now 9 is the root. And we're gonna move it into the sorted region and replace it with 1, shift it down, repeat the process until now our boundary is no longer greater than 0. And we move it into our sorted region, and our sorted region is now the full sorted array. Here, I'll declare a new variable called boundary. And at first, that's gonna be set as n minus 1. We're gonna repeat while the boundary is greater than 0. We're going to swap them. So I'm going to say in temp is array boundary. Array boundary is array 0. And array 0 is temp. So we're swapping the root with the last element in the unsorted region. Then we decrease the boundary by 1. And we call shift down on the array 0 as our index and the boundary. So now let's run this and see if it works. Eight elements. And you can see that it fully sorted and gave us our answer 1, 2, 3, 6, 7, 8, 9, 10. The complexity of heap sort is big O of n log n. And the reason is we make n calls to shift down, which at most iterates through the height of the tree, which is log n.